Hello, class. This is MO 869, Introduction to Autonomous Vehicles. Lecture 10, Review of Probability and Bayes Filter. Before I get into the lecture materials, I'd like to acknowledge a few things. A part of SLAM lecture material is prepared based on the robot mapping lecture notes by Cyril Stockness, and lecture notes by Professor Ki-Chun Cho was also used to prepare these lecture materials. And I would also like to acknowledge that Mr. Sangbum Woo contributed in preparing the SLAM lecture materials. So we are covering the SLAM relevant lecture materials in this module, and I gathered some of the existing lecture materials, as well as created a few lecture materials to come up with this SLAM module. So last time, so let's take a look at outline. Last time we covered up to here. We introduced you to localization problem in autonomous vehicles, and to introduce you to localization algorithm. We went over what types of informations are available for position estimation, and we talked about dead reckoning, we talked about H2map, we talked about perception, and we're going to learn using those informations. We're going to learn post-fusion algorithm from now on. Which has three main methods when it comes to pose estimation methods. First one is the most famous Kalman filter, and then the next is particle filter, and the last one is graph-based optimization method, which is developed based on the least squares approach. So let's take a look at the differences, what the differences are. If you compare these three approaches, they are somewhat similar, but they are different. First of all, the Kalman filter and particle filter has been derived or developed based on the Bayesian filter, which is the commonality between the first two methods. But the last part is somewhat different. It relies on the optimization algorithm. But there is difference between the Kalman filter versus particle filter. Kalman filter assumes a Gaussian probability model, but particle filter does not have that assumption, meaning that you can handle non-Gaussian probability models. So it's a more general filter that can be applied, but that doesn't necessarily mean it's always the best choice. It's usually computationally more. It's computationally heavy. It tends to be slower compared to Kalman filter. Kalman filter is really efficient and simple, but still powerful method filter. If we can model the problem, if we can formulate the problem under some of these assumptions. Let's move to the last third method, which is graph-based optimization. The graph-based optimization uses Gaussian assumption, but the problem formulation can be more general. So let's take a look at these three approaches. But before we get into these filters, we need to go through some of the more fundamental principles, basic theories behind those filters. So to understand those filters, we need to go through Bayes filter and least square methods. But in order for you to learn Bayes filter, we need to also cover probability theory and Markov property. So let's start with review of a probability, and we'll move on to Bayes filter. Let's start with basic rules of probability. I think this page is quite straightforward. It's a simple set theory. So probability of A. So please take a look at this Venn diagram. Probability of A ranges from 0 to 1. Union probability of union of A and B equals to probability of A plus probability of B minus probability of A intersection B. Simple. Probability of set A complement, and probability of set A equals to 1. And we can also get these equations from equation manipulation. So let's move fast to the next slide. So conditional probability. Given event B happened, the probability of A defined as P of A condition B. And P of A condition B equals probability of A intersection B divided by probability of B. And by moving this over to this side, we can also rearrange that equation and get this second equation, which is the same thing. So, and then if A and B are independent, then this is true. Probability of A intersection B equals PA condition B equals PA times PB. And chains of conditional probability is as follows. P of A1, A2 through AN equals probability of A through A minus 1 condition AN times probability of AN. So what that means is you can take one of this out to separate as a separate probability of that set, and then you can make that as a condition. Two variables. So here it's conditional independence. Two variables x and y are conditional independent if p xy condition z equals px condition z times py condition z. So that's called conditional independent. And this is equivalent to probability x condition z equals probability x condition z and y. And probability of y condition z equals probability y condition z and x. So what this means is, you can add y to the condition and it doesn't have impact on the x, and same goes with x as well. You can add x in the condition, and that's doesn't have impact on the y. But this does not imply p x and y equals p of x times p of y. So this does not imply that, okay? This is conditional independence. And then this is again basic review of random variable, discrete continuous random variables. X denote random variable. X take on a countable number of values, x1 through xn. P of xi is the probability that the random variable x takes the value xi. Continuous random variable, x is continuous value. P of capital X equals small x equals small p of x is probability density function. Sum of these random variable is always 1, meaning that if you sum all the probability over all xi, then that equals to 1. And same goes with continuous case, but because it's a continuous case, you need to integrate that over the random variable. Okay, let's talk about the Bayes theorem. This is the famous Bayes theorem. This is the theorem basically. P of A condition B equals P of B condition A times P of A divided by P of B. So how was this derived? Well, if you move this over to this side, then this becomes P of B, and then this also is P of A intersection B, so they are equal, right? So let's extend that further to our interest. Parentheses don't show up here. Okay. So this is how it's supposed to be. Okay. So this is from Bayes theorem. This equation. Okay, just different notation, where H is hypothesis, a proposed explanation for a phenomenon, and E is evidence, information indicating whether a belief or proposition is true or valid. So what that means is E is evidence, something that has happened or that is for sure. And then what happens, what is the probability that that you see the hypothesis, okay? So this is, so we are interested in this probability, okay? But why do we need this equation? Well, sometimes what if we do not know this probability? Then, but we do want to compute this value, then we can, what this equation is telling us is we can compute that value using these three terms, okay? Which is probability of evidence given the hypothesis. And the prior probability of the hypothesis, and the prior probability of the evidence, okay? So if we can compute these three, okay, then we can compute this, okay? Again, apologize for the math equation error. Please take a look at the PPT file, okay? This is supposed to be this, okay? Oops. Law of total probability, the prior probability of the evidence can be represented as follows. And so I'll talk more about this later in the following slides. But what this is saying is this, okay? We can usually this is easier to compute, but sometimes this is, what if this is not available? Then we can replace that value with based on this equation. So that is this, okay? So we just replaced E with this, okay? So this is now let's go back and take a look at this equation. So what that means is we have marginalization, and then we have law of total probability. So what this is saying is, in the discrete case, P of x equals to summation of P, x, and y, I, and summation that over for all yi. And then in the continuous case, you integrate probability of x and y over for all y. And if you apply the conditional probability, then you get this equation. And what this means is that once we can compute, if we know this value and this value, then we can compute P of x, okay, in both discrete and continuous case. And to help you understand, this is a visualization in the discrete case where we have y, which is we have 6 sort of equally distributed, and then we have x distribution, and then we can compute P of X by computing each area within different yi, okay? So that's basically what this means. And let's move over to Markov property. What Markov property states is Markov is a stochastic process, has a Markov property if the conditional probability distribution of future states of the process condition on both past and present values depends only upon the present state that is given the present. The future does not depend on the past. Perfect model, no approximation errors, independent noise, static world doesn't change. So this is the Markov assumptions. And in many cases, this is applicable, but not always. And what this is, the key to Markov property is actually erase that. The key is this. Okay. What this means is x of t depends only on so let's say current time is t, then x of xt plus 1 depends only on xt and ut. That's basically what it means. And it's not a function of xt minus 1, ut minus 1. And what that means is you may have different history, but if you reached same xt and used same ut, then what you get for xt plus 1 is identical. And in math, in mathematical form, that is, so this is missing here, okay? Oh, this is also missing. So what this means is you can remove this, all of this, and just left with t, okay? And same goes here, okay? T is gone. And Z is gone. All of this is gone, okay? And this is not a function of u because it's z. Z is only function of x. But for xt, it's function of xt minus 1 and ut, okay? So that leads to zt, okay? So let me stop here, and I will continue this rest of the lecture material during the discussion session on Wednesday. Okay? See you on Wednesday. Bye-bye. All right, let's continue with Bayes filter. So like I said, Bayes filter is the foundation for Kalman and particle filter. So it's good to review and know how Bayes filter is derived and how that extends toward Kalman filter and particle filter. So the goal is to compute probability of X given control input U and observation Z. And we want to actually compute this belief XT given probability of XT given Z1 to T and U1 to T. So this is general definition of belief, and the definition is described here. Belief XT is probability distribution over the state XT conditioned on all past measurements Z1 through T and all past controls U1 through T. Okay. Let's start from start with Bayes rule. This distribution is probability can now be described by this equation using Bayes rule, and then the denominator, this part, will be described with eta for simplicity. To make this derivation and the whole equation simpler to describe. So usually this value is going to be a constant, and you can think of that as normalization term. So going back to this the system dynamics, we did look at these two equations in prior slides, and by applying Markov property, we can remove many of these terms down to relatively simple term here. And next, we can now expand this term into this equation, which basically integrates so the goal is to compute PXT conditioned on these input and observations, and we can expand that term towards this equation using this relationship we learned earlier. So, and what this was we can make condition on y, and we need to multiply it by p, and if we integrate that over y, then we can compute px, and this is just application of that. Okay, that's the total probability we learned. Here, this is the y, and this term is py. So let's continue. Again, let's apply the Markov property, and that allows us to remove all the history terms, all of this. So we are only left with x t minus 1 and ut. So what that means is xt is a function of xt minus 1 and ut, and we saw that from this figure here. And then let's apply Markov property for this last term here, so that we can remove other terms, just like we applied before. And if you take a look at this term, this looks similar to this. And in fact, this term is belief xt minus 1. So initially, we wanted to compute belief xt, and note that belief xt can be described by, can be a function of belief xt minus 1. And what that means is this can become a recursive computation. So this belief x of t will be used in the next time step, which is t plus 1. Okay. So this is the base filter, and what this so this is the base filter, and what this physically mean would be this second term, the integral part corresponds to the prediction step using motion model. So given xt minus 1 and ut, we know xt if we use motion model. Of course, we also need distribution for that model, so that we can compute distribution or probability. So using that, we can compute, sort of predicted belief for prediction parts, which is here, this part. And then we are left with the correction step, which is P of ZT condition XT. So this one requires a sensor or observation model. So we want to find out distribution of ZT given XT. So we need to know the relationship between XT and ZT. So ZT as a function of XT with sensor noises, sensor distributions. Okay. So once we have motion model, sensor model, we can compute, we can do predictions, and then we can do correction part, and then compute the belief distribution, belief XT distribution. So that was derivation of a base filter, and then we looked into some of the physical meanings of each terms in the equation, and this is how the Bayes filter algorithm can be coded. This is sort of this is a pseudocode. Okay, so the given input would be belief X and D, and then you initialize eta, and then if D is an input for Z, then you carry out this part. Or if D is an action data item U in control input, then you conduct this part. So so what this is doing is so here so we had this prediction step and correction step, right? So so we for observation, in the case of observation input, we need to compute this belief eta and belief, and then if we have action input, then we need to compute the predicted part of the belief distribution. So that gives you this two-step process, iterative process, to help you understand this algorithm. This slide will try to visualize what's happening. Okay. So the Bayes filter is basically doing this prediction and update process iteratively. In the case of localization, we have different sensors, and this is just an illustration. Let's say you moved from one point to another and you want to find out where you are at. So you have initialization, and then you predict using your motion model, and then you update based on your sensor model and observations. So it turns out that it turns out that you have some error from the prediction model, and then you use motion model again to predict your next position, and based on the sensor input, you're going to update, and then so you're going to repeat this process. Okay. So this is basic concept of Bayesian filter applied for localization problem. Okay. And note that this is the general form for many of these filters. And you can see different branches coming out of the Bayes filter. And in this lecture, we are going to cover two most popular filters, which is Kalman filter and particle filter. So there's so again, we are going to cover three topics in this class. That's going to be particle filters and Kalman filter, and then optimization based SLAM. Okay. There's appendix. Please take a look, which describes the base filter a little in little more details. It should help you understand all the derivations and then what these equations mean. Okay, so let me stop here and move on to the next lecture.